All right, guys, Math 5500. Going to switch gears a little bit. Let's the focus of this video is to transition from the MLEs. We've looked at mass and density functions. We want to move into MLEs for regression. So what I want to do is I want to start out with some data, but for the first illustration. Again, you know me, I'm not talented enough to speak and write. So I want to start out with some with a data set. And the goal here is to calculate the likelihood that these data came from let's just say with the following parameter values. Let's say the beta 0 is equal to 0, beta 1.5. Let's say the variance is 9, so we know that the standard deviation is equal to 3. So what goes on here? First of all, and again, I chose these to be something easy, so we can just do mental arithmetic and not need something else. But anyway, what goes on here is if we think about the data, and so we have this line's intercept is 0. So let's say it looks something like this. If we take a look at the very first point at 20, and I'll do my best to draw a vertical line here. At 20, what we expect is we expect the y values to vary, right? For example, if we were predicting first year GPA from a student's ACT score, so the ACT score would be the predictor, and the high school GPA would be the response or the dependent variable. Well, for a particular ACT score, let's just say 22. We would expect the first year GPAs to vary. Well, the assumption in regression, this is kind of hard to do actually, is that actually that looks pretty good. I'm pretty impressed. That the responses are normally distributed with mean and variance. Okay, now the mean for this 20 can be found by, again, this tells us that y hat is 0 plus 0.5 times x. So I can put my x in and get my mean response. So in this case, the mean is going to be, what, 10? Now, this is a little bit clumsy. So let's bring this out and investigate it a little closer. So again, we're looking at the point 20, which has a mean of 10. So we have a standard deviation of 3, and although we really don't need this, it just gives us a little bit better indication of the distribution for the y values at x equal 20. So, but we know that 68% approximately of the cases, the measurements will be between one standard deviation below and one standard deviation above. Now, our focus is on this 5. So this 5 will have a density, and it should make sense that the taller the density is, the more likely it came from this distribution. Again, imagine having a point way out here. Well, the density would be very small because the probability of getting this point from this distribution. So it may be more likely that this point came from another distribution down here. But anyway, let's just go ahead and let the process play its way out. So now we kind of transition from regression into the probability density function of the normal distribution, because that models our responses of y. And I only say that because we looked at calculating densities for normal distributions earlier. So I'm going to go through this a little faster than I typically would, because again, it's covered in a previous video. So we know that we can do calculate a density by sigma squared root of 2 pi e to the negative 1/2. So y minus beta 0 plus beta 1 x over sigma quantity squared, right? For this point, we're going to have a standard deviation of 3, square root of 2 pi, e to the minus 1/2. So here we get y, which for the first case, let me see. So the y was 5. This turned out to be 10, which is just a mean. And the variance was 9. If we put this in our calculator, I did this beforehand because I didn't want to take up time. So is 0.0332. Now I can demonstrate that with R just by doing d-norm. So we want to calculate the density at 5 with a mean of 10 and a standard deviation of 3. So again, 0.0332. Now, going ahead and doing this for the rest, let's calculate the densities for all, and the maximum likelihood estimator would be the product of these densities. So we have d norm. Okay, so 12. The mean would be what, 27.5. Since the x value is 55, 55 times 0.5, 27.5. And again, variance is 9. So the next is 10. Mean is 15. Standard deviation 3. So we get a value of, insert 9 zeros, so 0.00, pretend I said 9 zeros, 2, 3. So not as likely. Now really in isolation, these densities, the product of these densities doesn't tell us a lot. So what we could do is we could shift our B0s and shift our B1s to assume other values and determine which seems more likely. So if the likelihood for another set, let's say for example that we decide to try 1 versus and just put a 2 there, just to kind of talk it through. So let's say we tried, instead of 0, we tried beta 1 equal 1 and beta 1 equal, whatever, beta 2. Then we would come up with another likelihood, and we could compare them and really find out some stuff. All right. Let's move on. All right. What I want to do now is I want to move on. I'm trying to stay a little bit organized here. Move into MLE for regression. And I don't think we're going to need R anymore, so let's get rid of it and go full screen here. All right, give you a little better viewing of what I want to do. Twist that a little bit where it lines up. Okay, and I want to illustrate this for the simple linear regression case. We're not in multiple regression yet. So essentially what we have is we have a relationship between x and y. So we've Again, collected some data. We'll eyeball it. Does it appear linear? Does it appear positive? Is it strong, weak, or moderate? Things we've discussed before. And then we want to examine the model y hat equals beta 0 plus beta 1 x sub I plus an error term. Now, just a sidebar here. This is not to be confused with, well, it is confused with. The reason I'm pointing it out here. Make sure you understand the difference between these two. And the difference is this. This is the predicted value, and we find the predicted value, this is the notation for predicted y. We find the predicted y by inserting our x into our model, and that's our predicted value. But this y right here is the actual observed y. And to make these equal, we have an error term. We have to add or subtract something. Visually, you can see it like this. Let's just choose something really simple. So I have an x term right here. If I put this x term into my model, then I get that value right there, which is the predicted value. But if I look at the difference between okay, I've got my x and my y, which is right here. Well, I have to have an error term here to actually make those two equal. Because this essentially is what? This is just y hat. So to make my y hat and my observed y equal, well, there's typically some space in here that has to be added or subtracted, and that's precisely what the error term is. All right, I want to start with a new sheet of paper because I'm going to have a lot of stuff going on here. So let's just start bare bones and let's talk about some assumptions. First of all, the errors, which are the E sub i's, we assume to be normally distributed. Mean zero, excuse me, and with variance, constant variance. Now, what does that tell us? That tells us that if we go back here, that tells us at this 55, which would be out here someplace, that this distribution is going to have the same variance as with x equal 20. So we have constant variance, sigma squared, and the errors are independent and identically, excuse me, identically distributed. Now, for MLE, right? If we're doing MLE, we need to, trying to think where I want to take this. Okay. We need to address what is the distribution of our y's. Now, imagine back the illustrations we've done before, like the binomial and Poisson, and I think I did normal distribution. Imagine trying to calculate an MLE without knowing the probability distribution. Well, good luck with that, right? So we need to know the distribution of our y's if we're going to focus on the y's. We need to calculate the MLE. It's as simple as that. So the first thing I'd want to do is look at the expected value for the y sub i's. And of course, this is just from previously, the y sub i's, again, from back over here, is beta 0 plus beta 1 x sub I plus the error term. Now, beta 0 and beta 1 are parameter values, so we can just consider those to be constants. And the x sub I we consider to be a constant as well. So we can pull those out. and look at the expected value of our errors. Well, we know that the expected value of our well, the expected value of our errors uh, is equal to 0. So the expected value for y, its mean, quote unquote, is b0 plus b1 x sub I. Next thing we'd want to look at is we'd want to look at the variance for our y sub i's. So this is equivalent to the variance for our beta 0 plus beta 1 x sub I plus, of course, our error term. From the same logic of 4, constant, constant, constant. So we have the luxury of pulling those out and focusing just on the variance of our e sub i's. Well, the variance of our e sub i's is just going to be 0. I think, stated that before, right? No, I'm sorry. Variance is sigma squared. So the variance here is sigma squared. Of course, these are going to be 0. So the variance for the y sub i's is just going to be equal to sigma squared, as we thought before. So what else? Okay, we need the distribution. Normally distributed, positively skewed, binomial. What is it? So again, referring back to we can think again, constant, constant, constant. So a constant distribution, we just kind of control for that. And then we know that the error terms are normally distributed. So when we have a constant plus something that is normally distributed, it forces our y sub i's to be normally distributed. So we know that follow a normal distribution with mean, as we showed up here. Extremely annoying. Apparently I need ink. Imagine that. Okay, I lost my train of thought. So, okay, we have normal distribution. We need mean x sub I. And we have variance sigma squared. All right. I'll tell you what. I think I am going to end the video here and then start with the next video. Start up with the next video. All right, take care.